Section 1.2.3 Networking, VPCs, Subnets, and Routing. The Mental Model. Let me start with a situation many engineers recognize. Everything is working. Traffic is flowing. Users are happy. Then someone makes a small networking change. Nothing dramatic, just a root update. Just a security rule tweak. Minutes later, half the system is unreachable. No errors in the code, no crashes, just silence. This is how many real cloud outages begin. Not with broken logic, but with traffic going somewhere it shouldn't. That's why networking has a reputation. It's quiet when it works, and brutal when it doesn't. If you talk to experienced engineers, you'll notice something. They don't rush networking decisions. They slow down, because they've seen what happens when assumptions turn out to be wrong. This is why interviews care so much about this topic. Not because networking is abstract, but because it reveals how you think about systems. If you can explain how a request travels from a user's browser to an application running inside the cloud, calmly and step by step, you already sound like someone who has been there before. That's the mental model we're building here. Every cloud system starts with a private network. In AWS, it's called a VPC. In Azure, a VNet. In Google Cloud, also a VPC. Different names, same concept. Think of it as your own private neighborhood inside the cloud provider's massive city. By default, no one can see inside. No traffic enters, no traffic leaves. You decide where the doors are. When you create this network, the first thing you choose is its address space. Something like 10.0.0.0/16. At this moment, it feels like paperwork. Later, it feels like destiny. That address range defines how big your network can ever become. And when systems grow or companies merge, overlapping address spaces turn simple connections into months of work. Then you divide the network into subnets. And here's a rule that's worth burning into memory. A subnet always belongs to exactly one availability zone. You can't stretch it across zones. You can't cheat. This isn't a limitation. It's protection. Availability zones are designed to fail independently. By keeping subnets inside zones, the cloud forces you to spread risk. If one zone disappears, your entire system doesn't go with it. Now comes the concept that causes more confusion than almost anything else. Public and private subnets. Here's the part people miss at first. A subnet is not public or private by nature. It becomes public or private because of routing. That's it. If its route table sends internet-bound traffic to an internet gateway, it's public. If it sends that traffic to a NAT gateway instead, it's private. One line in a route table. This is why two subnets can look identical, yet behave completely differently. That single decision decides exposure. This is often the first real aha moment. Suddenly, diagrams stop being mysterious. Public subnets sit at the edge. Private ones live behind them. In real systems, public subnets are boring on purpose. They host load balancers. They host NAT gateways. They don't host business logic. Private subnets are where the real work happens. Applications run there. Databases live there. Kubernetes clusters usually operate there. These systems don't accept traffic directly from the internet, but they still need to talk outward. They download updates. They call third-party APIs. They pull container images. That outbound traffic flows through a NAT gateway. The NAT lives in a public subnet, acting like a one-way mirror. Private systems can see out. The internet can't see in. This design has saved countless systems. And yes, NAT gateways cost money, which is why experienced teams learn quickly to avoid unnecessary NAT traffic. For cloud services like object storage, they use private endpoints, so traffic never touches the public internet at all. Now we reach the quiet center of everything. Routing. Every subnet has exactly one route table, and that table decides where packets go. Routing doesn't scream when it's wrong. It just fails quietly. Networking problems rarely slow systems down. They usually stop them. A single missing route can turn a healthy system into a black hole. That's why senior engineers treat routing changes with respect. They don't just try something. They review it, they test it, they roll it out carefully. Many long debugging sessions eventually end with a sentence like, "Oh, the route was wrong." Private instances don't talk to the internet directly. They go through NAT. Inbound traffic only reaches them if explicitly allowed. One of the most common mistakes is assuming that private automatically means safe. When this model is clear, networking problems become logical. When it's fuzzy, everything feels random. As systems grow, traffic patterns grow with them. Services talk to other services, VPCs talk to VPCs, regions talk to regions. On-premise systems talk to the cloud. This is where familiar building blocks appear. Internet gateways, NAT gateways, VPC peering, transit gateways, VPNs, private endpoints. Different providers package these differently, but the ideas never change. Once you understand flow, switching cloud platforms stops being scary. Many security incidents didn't happen because encryption failed. They happened because something powerful was placed in the wrong subnet. A database that didn't need to be public. A service that trusted the network too much. An assumption that no one would ever reach it. That's why some companies take a very defensive stance. Minimal exposure. Private by default. Very few entry points. These patterns weren't invented in textbooks. They were learned after things broke. Networking isn't about memorizing services or acronyms. It's about understanding movement. If you can picture traffic entering the cloud, passing controlled gateways, flowing through load balancers, reaching private systems, and leaving through defined exits, you understand the backbone of cloud architecture. This is the kind of explanation interviewers are really listening for. With networking clear, the next question naturally follows. Once traffic arrives, how do we distribute it reliably and safely? That's where load balancing comes in. End of section 1.2.3, Networking.